Hello viewers, today I will talk about some problems and their solution on organic photochemistry, and this is the set 1 and I will bring another set of problems. So these problems and their solutions are very important for IIT-JAM or GATE, and also for CSI NET, and also for PG entrance exams at different universities or institutions. So these are very important in that sense. Okay, so I already had shared with you a full course on photochemistry. Now these are related to their problems and solution, which will be appearing in the competitive exams. So let's see what we have. So the first problem deals with the dye-none system, as you can see over here, which upon photoirradiation first produce a compound which is represented as a question mark inside the box, and which upon further irradiation, photoirradiation will produce an aromatic compound. So this can be either the following way, what the way it is represented here, or there can be the products and the other products which are wrongly represented if it comes as a multiple choice question. So both are possible. So first we need to know the answer of the question. Okay, so next I will go to the problem's solution, and with mechanism we will describe how this dye-none system under photoirradiation eventually ends up with forming an aromatic compound. Let's see. So this can be the whole route where this dye-none system eventually end up with a cyclopentanone system, and which upon photoirradiation ends up the diphenyl substituted phenol system. Okay, so here the reaction will proceed via the following pathway, and allow me to tell that here, if you look carefully, that the beta and gamma positions of the carbons, just let me tell you. So this should be the beta position here, and this one the gamma position, of course, with respect to the ketone, and then these carbons will exchange eventually, and there are several steps for that. The first step involves the intersystem crossing, and of course that comes after immediate excitation of this dye-none parent molecule, and the transition from N to pi star takes place. Okay, so with the intersystem crossing, it comes from the ground state S0, it goes to S1, and from there on it goes with the intersystem crossing. We get the compound, this diradical, the oxoradical, in the triplet state. Okay, which can rearrange further via the resonance, and we can have this radical, the beta radical, as again. Then in the second step, here this beta-beta bonding takes place, you see. So if we say that this one is the beta 1, this is the beta 1, and this is also eventually the beta bond, beta carbon. So eventually these two will be the beta-beta bonding, and that will go on the radical combination, and eventually end up with formation of the 5-member cycle fused with a cyclopropane ring, which is eventually substituted with 2 phenyl groups. Okay, and then in the next step, another intersystem crossing will take place to form the carboniums, and these carboniums are usually occur from the N to pi star transition. Okay, so and these carboniums eventually undergoes double 1,2 shift, and we get our first photo product as the cyclopentanone fused with a cyclopropane ring, which is substituted with 2 phenyl groups. Okay, so this is the first stage of the reaction. In the second stage, when that first photoadduct product eventually exposed under more photoirradiation or light undergoes to produce the 2,3-diphenyl substituted phenol, the aromatic compound. Now for this one, the mechanism will involve again another intersystem crossing, and the transition from N to pi star will give the enolate radical, and in which the cyclopropane ring eventually will rearrange, because in the cyclopropyl carbonyls when conjugated with the enolates, they rearrange very rapidly. We know that. So in that case, that will happen again, and we will end up with the radical here with the 6-membered ring, and again the biradical intermediate, of course. That will eventually undergo intersystem crossing again to form the carbonium cation, the carbonium intermediate, involving the N2 pi star transition, just in the previous case. So we will get these carboniums, and then the aryl migration need to happen, and that will lead eventually to the formation of the aromatic compound. So this is the whole pathway for the generation or for the course of the reaction, when the first product of photoirradiation of this dienone system further involved or further exposed on photoirradiation. So next we will be talking about the second problem, and here this is a 1,4-dihydro 1,4-methano naphthalene substrate, what you can see here, and here you see that this can be considered a dipymethane system, and in presence of H nu and sensitizer, what should be the product? Okay, so this is of concern. So let's see how the reaction proceeds. So eventually from the 1,4-dihydro 1,4-methano naphthalene, we will end up with the methano-cyclopropano indene compound as the product in presence of H nu and sensitizer. Okay, so here this dipymethane rearrangement will take place, and we see that first, as we know, the pi bonds are, when photo irradiated, they form the biradicals, and then from there on the radical rearrangement or recombination takes place in the following way, and these are the intermediates that eventually ends up with the methanocyclopropano indene derivative as the final product. I hope you don't have any problem understanding the mechanism of the course of the reaction, the probable course of the reaction, because it's with the arrows, it's been explained or represented in a very easily understandable way. So this was the second problem and its solution. Now I will go into the third problem, where the substrate is a substituted cyclopentanone system, and in presence of tertiary butanol and light, the photoirradiation of wavelength around 390 nanometer, what should be the product? So this is our next problem, problem number 3, and here the substituents are methyl and phenyl groups. So let's see how it proceed with the mechanism for that. So first, the product with the phenyl and methyl substituted cyclopentanone compounds, pentanone compound in presence of tertiary butanol, it will eventually produce the tertiary butyl substituted phenyl pentanoate derivative. Okay, so this will be the major product, and the course of the reaction will involve, first the phenyl ring will involve into the radical reaction following the cyclopropane ring formation, and the enolate radical will be there generated as the intermediate, which eventually rearrange to form a cyclobutanone ring fused with the cyclopropane, and that further substituted with a phenyl group. Okay, so that will be another intermediate, and please have a look at the stereochemistry of the methyl and hydrogen atom, which are attached at the junction of the 5-membered ring and 3-membered, and eventually in the second intermediate with the 4-membered and 3-membered fused junction. So that is very important. Next, that can rearrange again this fused 4-membered and 3-membered fused ring structure can rearrange again to form this ketene, phenyl substituted ketene, and then in presence of tertiary butanol solvent, it will ends up with tertiary butyl substituted phenyl pentanoate derivative. So here, if we use this alcohol kind of solvent, it is need to understand that if we use this alcohol kind of solvent, it will eventually going to end up with the formation of the esters. Okay, so with the alcohols we will get the esters. So it depends on the solvent that is used as the terminal product. So that is very important. You need to take care of that. Next, we will talk about a classic problem of the application of oxidipymethane photoisomerization reaction, where you can see the substrate is a nitrogen containing bicyclic system, which eventually a substrate of oxidipymethane system, if you can recognize from the skeletal structure. And this is more commonly known as quineuclidinone. So the substrate is the quineuclidinone. You can see, substituted quineuclidinone, and on photoirradiation of wavelength of 350 nanometer, and in presence of the mixture of solvent of acetophenone and acetone in a ratio of 5 is to 95 or 1 is to 19, whatever way you want to represent, eventually produce one compound which is marked here inside the box as the query mark. And upon lithium dimethyl cuprate, this will produce another product. So what can be the product, we will see, and we will follow the mechanism how the products can be obtained. Let's see. So here is the full course of the reaction. If you can see that the quineuclidinone first on photoirradiation and in presence of photosensitizer and the solvent mixture of acetophenone and acetone will yield the cyclopropane fused pyrrolizidine compound, which is itself is very important and present in numerous biologically active alkaloids. So this is first fused with cyclopropane ring, and then in presence of lithium dimethyl cuprate, the reductive cleavage takes place of the cyclopropane ring, and we end up with finally the pyrrolizidine compound, the substituted pyrrolizidine compound. So let's see how the mechanism proceeds. So first, the quineuclidinone, first the oxidipymethane system undergoes the photoirradiation, forms the radicals, corresponding radicals, and the cyclopropanation proceeds over there, which further rearranges to give the cyclopropane fused the pyrrolizidine compound, and upon reaction with lithium dimethyl cuprate, it will yield the single diastereomer, as you can see in the extreme right hand side, first the keto form, and which eventually will tautomerize to the enol form. Okay, so the second step will be like this way, that the cyclopropane fused pyrrolizidine compound will the reductive cleavage of the cyclopropane ring will take place in presence of lithium dimethyl cuprate, and the keto form, as you can see, can are enolizable. So this ketoenol tautomerism will take place eventually to end up with an enol form. Okay, so the final product can be either the keto form or the enol form, but that will be eventually that depend on the options that you get during the exams. Or if this is the straightforward way, you can either write the ketone and the ketone as this is enolizable, so this can undergo the tautomerization and form the enol isomer as well. So eventually, so from the quineuclidinone we get the pyrrolizidine compound, which is biologically very active. So this example is a very important one, and you should check it very well. So our next problem is about the diazoketone substrate, and this is also the two diazoketone compounds you can see here, and both the compounds when undergo the substituted alkyne, the triisopropyl silyl ether substituted the alkyne substrate in presence of photoirradiation and 1,2-dichloroethane solvent, and from room temperature to 80 degrees centigrade, the long span of heat as well, it will end up with the tricyclic compound. And what should be the structure of the tricyclic compound and how the reaction will proceed, so we will see that next. So this is the overall reaction in at a glance. If you can say that the diazoketone, the benzo-fused the diazoketone compound, upon reaction with the alkyne system, pi2 system, in presence of H nu, and the reaction condition will end up with the tricyclic compound, which is nothing but the substituted dihydrophenylene derivative. So this substituted dihydrophenylene derivative can be obtained from both the isomer, and they will end up with single product. Here we need to understand these diazoketone compounds are very prone or easily form the carbene. So here both the carbene that have been generated from each isomer of the substrate eventually end up with the, by means of Photo-Wolff rearrangement, with the single ketene isomer. Okay, the bromo substituted ketene isomer. So this one is a unique product from the both the carbene that can be generated from both the substrate isomers. And then this will go the 2+2 cycloaddition reaction with the alkyne substituted alkyne system, and ends up with a six-membered fused spido cyclobutenone ring structure, which is eventually substituted with the isopropyl group and tri-isopropyl silyl ether group, the olefinic part, of course. And then, because this is the four-membered, this four-membered enone ring structure is quite strained, so it will go further 4-pi electrocyclic ring opening, and we will get a rearranged ketene again. Okay, so this one further will undergo the 6-pi electrocyclization reaction, followed by tautomerization or tautomeric reaction, and eventually they will end up with the substituted dihydrophenylene derivative. So this is an example how the diazoketones react to form different compounds involving the electrocyclization process. Okay, so this is a classic example for that one. So now next we will move into the next problem, which is about the dibenzothiophene, if you can see over here, and what will be the product of dibenzothiophene when irradiated, the photochemical irradiation takes place. So if you can see here inside the circle, the blue dotted circle, it is an example of the dipymethane rearrangement system as well, and here it involves the heterocycles. Okay, a thiophene here for concern, the benzothiophene, the dibenzothiophene system. Now in such cases, the typical biradical intermediates will form, and we will see in the solution cases. So first the biradicals will be generated, and eventually they will arrange to go for the radical combination of these intermediates, and they will undergo the photochemical rearrangement to form the cyclopropane ring structure first, which upon cleavage again form another biradical, which ends up on combining with each other, producing the cyclopropane ring structure, and which is fused with the benzothiophene, one of the benzothiophene ring. And the cyclopropane ring is further substituted by a phenyl ring, which was first from the beginning flanked from the methylene carbon center. So this is the product, and one important thing that we need to understand, that the structure or the substrate structure provides a photochemical rearrangement, and that can also undergo a tri-pi-methane photoisomerization as well. So there is a provision of this tri-pi-methane photoisomerization reaction for this substrate. So here it is about the dipymethane rearrangement reaction. It can be also for further can be applied for the tri-pi-methane photoisomerization reactions also, because the substrate gives the provision for that. So this was the sixth problem. So I will be talking about the next problem. Let's see that. So this is a very classic example of Norris type reaction, Norris type 1 reaction, to specify further, where a bicyclic ketone, you can see over here, with substitution undergo photo irradiation of wavelength of 254 nanometer in presence of room temperature for 17 hours in acetonitrile, and going to end up with the first product, which is marked as the query mark inside a box in 90% of yield, and that product further on reaction with pyridinium chlorochromate in presence of dichloromethane, and secondly with palladium in charcoal in presence of hydrogen is going to end up with the natural product, the Bosnia lactone. Okay, so this is a process of involving Norris type 1 reaction in the synthesis of naturally occurring products. Okay, so let's see how the reaction will proceed. So first you can see that the bicyclic ketone system will undergo the photoirradiation reaction. So photochemical rearrangement will take place, the Norris type 1 rearrangement will take place, Norris type 1 reaction will take place, and we will obtain the cyclopentene fused tetrahydropyran 2-ol, that compound which is represented in the middle in the box. Okay, and then with the conditions, first and condition of an oxidation reaction, and secondly of a reduction reaction, will end up with the natural product Bosnia lactone. Okay, so we see first as a typical process for the Norris type 1 reaction, which is nothing but an alpha scission process. That is, the alpha bond to the carbonyl compound will cleave and produce the biradicals. Here you can see the biradicals, and with the red arrows you can see how the biradicals will react with each other and recombine to form the terminal aldehyde and the olefin, of course, which upon further reaction or cyclization eventually end up with the tetrahydropyran 2-ol derivative. Okay, so this tetrahydropyran 2-ol derivative then undergo oxidation reaction first. That is, the 2-degree alcohol will be oxidized to the ketone, producing or making it a lactone, and the olefin which is present in the fused cyclopentane ring, that will be reduced, and we will get a cyclopentane ring only. So eventually that will end up with the formation of Bosnia lactone as the main product. So this is an example of Norris type 1 reaction which is used for the formation of a natural product. So thank you for watching my channel TG Chemistry, and keep watching my channel. And if you like the videos, please don't forget to subscribe my channel and press the bell icon to get the notification for further videos that I will bring regarding photochemistry and also regarding other chemistry aspects, which will be very important or useful for the students who are appearing in competitive exams. Thank you.